Ever wondered where half the universe's baryons went? First off, what are baryons? Baryons are particles like protons and neutrons that make up most of the matter we can see and touch. In the early universe, right after the Big Bang, scientists could estimate how many baryons were around by looking at the cosmic microwave background and conducting Big Bang nucleosynthesis studies. These studies tell us baryonic matter should make up around 4.8% of the universe's energy content. But here's the catch. When we look at the more recent universe, we can only account for about half of those baryons. Where did the rest go? This discrepancy is what we call the Missing Baryon Problem. You might think, isn't this just like dark matter? Well, not quite. Dark matter is non-baryonic, meaning it's made of stuff other than protons and neutrons. The Missing Baryon Problem specifically deals with baryonic matter that we know should be there but can't see. So, what happened to these missing baryons? One possibility is that they're hiding in the vast cosmic web, an enormous network of gas filaments stretching between galaxies. These filaments are very diffuse and difficult to detect with traditional methods. Recently, scientists have been using space telescopes like the Chandra X-ray Observatory to search for these hidden baryons. By observing the light from distant quasars as it passes through the cosmic web, they can detect the subtle signatures of these filaments. And guess what? They found some of them. But the mystery isn't completely solved yet. Researchers are also exploring other avenues, like looking for baryons in the hot gas surrounding galaxies, known as the circumgalactic medium. This hot gas glows in X-rays, which means space-based X-ray telescopes are key tools in this hunt. Let's take a step back and understand how we even know how many baryons should be in the universe in the first place. This knowledge comes from two methods that give us a glimpse into the early universe. First up, we have the theory of Big Bang nucleosynthesis. According to this theory, higher numbers of baryons in the early universe should result in higher ratios of helium, lithium, and heavier elements relative to hydrogen. When scientists compare these predictions with actual observations, they find that the abundance of baryonic matter should make up between 4 to 5% of the universe's critical density. This agreement between theory and observation is a crucial piece of the puzzle. But that's not all. We also have another powerful tool, the cosmic microwave background. This is the afterglow of the Big Bang, a faint cosmic radiation that permeates the universe. By analyzing the small fluctuations or anisotropies in the CMB, especially the second peak of the CMB power spectrum, scientists can infer the amount of baryonic matter. Baryonic matter interacts with photons, leaving a visible imprint on the CMB. Let's turn our attention to the late universe. The density of baryonic matter can be obtained directly by summing up all the known baryonic matter. This task is highly non-trivial because although luminous matter such as stars and galaxies are easily summed, baryonic matter can also exist in highly non-luminous forms, such as black holes, planets, and highly diffuse interstellar gas. Nonetheless, scientists have developed a range of techniques to achieve this. One such technique involves the use of the Lyman alpha forest. This method relies on clouds of diffuse baryonic gas or dust that become visible when backlit by stars. Another technique is gravitational microlensing. If a planet or another dark object moves between the observer and a faraway source, the image of the source gets distorted. The mass of the dark object can be inferred based on the amount of distortion observed. Additionally, we have the Sunyaev-Zeldovich effect. This phenomenon occurs when CMB photons interact with free electrons, leaving an imprint in the CMB. Before 2017, baryons were found to be distributed as follows: 10% inside galaxies, 50–60% in the circumgalactic medium, and 30–40% unaccounted for, thus accounting for about 70% of theoretical predictions. Large-scale galaxy surveys in the 2000s revealed a baryon deficit, leading theorists to re-examine their models and predict that gas must flow between galaxies and galaxy clusters. The census of known baryons in the universe tallied to around 60% of total baryons until the resolution of the Missing Baryon Problem. This is in distinction from the composition of the entire universe, which includes dark energy and dark matter, of which baryonic matter composes only 5%. Around 7% of baryons exist in stars and galaxies, while most of it exists around galaxies or galaxy clusters. The Lyman alpha forest contains around 28% of the baryons. the warm phase of the warm-hot intergalactic medium was detected by soft X-ray absorption in 2012, establishing 15% of the total baryon content. The intra-cluster medium accounts for around 4% of total baryon content. It is composed mostly of ionized hydrogen and constitutes about 10% of a galaxy cluster's total mass, with the rest being dark matter. Radio telescopes, such as the Very Large Array in New Mexico, allow astronomers to capture the faint signals emitted by hydrogen atoms in the early universe. X-ray observatories like Chandra and XMM Newton have been instrumental in detecting the hot, ionized gas that makes up the warm-hot intergalactic medium and the intracluster medium. Spectroscopy, the study of how matter interacts with light, is another powerful tool. By analyzing the absorption and emission lines in the spectra of distant quasars, scientists can trace the presence of baryonic matter in the Lyman alpha forest and the circumgalactic medium. However, these methods come with their own set of challenges and limitations. But with advancements in technology, such as the James Webb Space Telescope and next-generation radio arrays, we are on the brink of a new era of discovery. While the missing baryon problem remains one of the most perplexing issues in modern astrophysics, in 2017, two independent groups of scientists claimed they had found evidence for the missing baryon's location within the intergalactic medium. These baryons were hypothesized to exist as hot, diffuse strands between galaxy pairs in the warm-hot intergalactic medium. However, detecting these strands is no simple task. They are not sufficiently hot to emit X-rays, making them elusive to conventional detection methods. Instead, the scientists employed the thermal Sunyaev-Zeldovich effect, which measures the density of these strands by observing how light from the cosmic microwave background scatters off them. This scattering causes very faint patches in the CMB, which are too dim to see directly but become detectable when overlaid with the visible galaxy distribution, showing that these strands could account for about 30% of the baryonic density, precisely the amount needed to solve the missing baryon problem. However, even if these findings are accurate, they only describe the distribution of baryons between nearby galaxies and do not offer a complete picture of cosmic gas in the late universe. In 2021, another study proposed that approximately 50% of all baryonic matter exists outside dark matter halos, filling the vast spaces between galaxies. In conclusion, the missing baryon problem remains one of the most intriguing mysteries in cosmology. Despite significant advancements in technology and observational techniques, a large portion of baryonic matter in the universe remains undetected. Scientists continue to explore various methods to locate this elusive matter, and each discovery brings us closer to understanding the true nature of our universe.